Okay, my PChem people had better not screw up answering these questions.
Don't worry, we won't.
Yeah.
We simply just won't.
So, Adriana, where is the ground state of my hanging weight spring system here? All right, where, meaning exactly, I could have this thing going. Where's the ground state?
The ground state is when it's compressed without the weight or with the weight?
You can't remove the weight, otherwise you change your system.
Ground state is like that. The ground.
It's in between.
Ground state is, well, it's location, right? It's not vibrating right now, but it's a lot easier to see its ground state if I don't have it vibrate, right? Because that's it, right here,
It's just, yeah.
right here. This is it, right? That is its ground state. Now, here's what we're really talking about, right? This is what we're talking about, but where is its ground state? You have to almost have a video camera or in your head or whatever and take a picture right when it's right there. Right? Okay. Yeah. Okay. Using spectroscopic jargon, how could the spring be excited? Using spectroscopic jargon, what does the spring have to do? Absorb. Oh, and since we're talking about vibrational energy, absorb what part of the electromagnetic spectrum? IR, right? Infrared. So he absorbs some IR, and then this happens, right? But if the spring represented a chemical bond, which is what we want it to do, okay, carbonyl bond, I don't care, could I pull the weight down any distance? What do you think there, Alice? If it represents a chemical bond, could I pull it down any distance I wanted? Why? She said, wouldn't it be a certain extent? Okay, well, you're right. There's a certain maximum distance, and then things are going to fall apart on you. So you can only stretch things so far. But don't think in terms of length. Think in terms of what? When I'm pulling this spring down, I'm giving it... we just said how we can get excited. It's absorbing what? It's absorbing IR, which is energy. All right. So can this bond be pulled down or stretched any distance we want? So it'll absorb any energy it wants? If you go up to the FTIR, isn't there a big table of all these different frequencies for different functional groups? Right? Those are all different bonds. Is there more than one frequency for each of these different? No, just one. That's how you know it's a carbonyl that absorbs this energy, right? And you can replace the word energy with wavelength. You can replace the word energy with wave number. You can replace the energy with frequency, right? All those are the same thing. They just all describe one energy. So back to the question. If the spring represents a chemical bond, can I pull it down any distance I want? No. And that's what's very, very odd. Here, I mean, you can't imagine it. You really can't. I can pull this down any distance I want and get her to vibrate. No big deal. But if it's a chemical bond, no. Man, it's only certain energies. Even though, no matter how far I pull it down, Rob, it's always the same what? It's always the same frequency. And you got to sit there and physically count it if you don't believe it. Pull it down like that. Pull it down a little dinky bit. It's the exact same frequency. Okay. So, okay. So what does, in our little chemical equation here, what does H nu represent? Paulo, what does H nu represent? H nu, a photon. H is what, everybody? PChemers? Planck's constant. Nu is, what's nu, Adriana?
Not old.
So it's then F. Frequency.
I was like,
Right.
I know what it is.
Okay, it's frequency. How about this M and M star? Kathleen, what's going on there? M and M star?
Oh,
What's M and M star? You have M
It's better not.
strikes H. They're both. It's M is a reactant with H nu, and then it turns into M star. What's the difference? Yeah. This isn't PChem stuff. This is instrumental analysis. Are you using the FTIR?
Yeah.
Are you using the UV Vis?
Yeah.
All these are interactions between what and what?
Light and stuff.
Where is that in this equation? Where's light and matter?
M is matter.
There's your matter. There's your light. Right? That is spectroscopy. Okay. So what's the difference between M and M star? They both have to be what? Matter, a molecule. But one is, which one has absorbed some energy? M star. M most likely, so the technical jargon is M star is in its what state? Excited state. M is in its G word, ground state. M is in its ground state. Okay. Okay. So which excited state? We don't know. It's just has a little star on it. So it has higher energy than the ground state. It's an excited molecule. Okay. So what is an excited molecule? Right. So from PChem, we know that this is PChem. This instrumental doesn't have to worry about. This actually is the ground state. There is no such thing as a 0-point energy. Okay, so this actually is the ground state. So take PChem if you want to get more into that. But the point is if this is the ground state, then this is an excited state. This is an excited state. All right. Now the problem is I can pull it down any distance I want, but if I couldn't, okay. Do excited molecules always return to their ground state? John, do excited molecules always return to their ground state? If they didn't, what would be the consequence? You could only do an analysis how many times? Once, right? 'Cause it absorbs. Everything's in the excited state. It can't absorb anymore, right? Okay. All right. So on it seems like stuff has to return to the ground state, right? How? What is that excited molecule doing that it wasn't doing before? Or was it doing differently? Would be a better way to state it. What is it doing differently? What increased? All right. Yeah, better words. It starts with an A. AM of its vibration. Amplitude, right? It's energy, right? But since we can see it, we can use the word amplitude. It's vibrating with a larger amplitude. Same frequency, but it's vibrating with a larger amplitude. So how does it go back to this? Yeah, it has to lose energy, but how? How? Well, it absorbed, right? That's how it got there in the first place. But everything, and really quickly, gets back to that. Yeah, it's hitting a bunch of other stuff, right? This is probably, since we're talking about our analyte, maybe it's a carbonyl, since I like to think of that carbonyl as like a sharp peak in the FTIR, right? And it returns to its ground state, but it's our analyte. There's a whole bunch of what around this thing? The M word, matrix, which consists of solvent molecules and all this other stuff. But then you also have the dang wall of the container. So this stuff is vibrating with a much larger amplitude, but it's going to be striking stuff the whole time, right? It doesn't really get tired. It just gives up its energy, right, to everything around it. And it's called vibrational relaxation. Vibrational relaxation is a word that we're supposed to use. But a better word might just be what? It starts with an H. It generates what? Heat. It just generates heat, right? And there's no way a little cuvette is going to feel hot to you, right? I mean, we're talking about such a small amount of energy. It can't increase the temperature of the water. That takes a lot of energy. There's a huge heat capacity there. But in a very local microscopic environment, yeah, the temperature went up, right? Because this little guy's vibrating faster. Think about it that way, right? He gives up his energy to the stuff around him. Well, the stuff around him then has to start moving faster, right? Okay.
Does that happen like quickly?
Really quickly. It has to.
I mean, like, that means like a molecule can only stay excited for a very, very short.
Yes, and we're going to get into this time concept by the end of the hour.
So how much
Okay.
of that energy do they actually end up spending?
I think, again, we'll be able to quantify that by the end of the hour. To answer those questions, just how much energy is given up, how fast all this stuff happens, those are good lead-in questions for what's coming up. Can a molecule, Sandy, or atom, for that matter, since we're going to be talking about atomic absorption spectroscopy, the AA and the flame, right? Can a molecule or atom absorb any amount of energy? No, you're supposed to use the word, well, the PChemers are supposed to use the Q word. Energy is quantized, yeah. Right? But it's just like we said here with the spring. We can't give it any energy we want. There's only certain set energies. Okay. The diagram to the right depicts an emission event. Well, Emily, what's the difference between an emission event and an absorption event? What would you say? Absorption event, emission event. Absorption, you're gaining energy. Yeah, okay, good. In fact, in an absorption, this molecule is starting in its what state? Ground state, going to an excited state. Emission event, it's starting in its excited state and going to its ground state. Okay. Okay. Again, what answer? Couldn't it just go to a lower excited state? We're going to answer those questions, and you'll see. All right? Hang on. So what he's saying is, Rob's question is, couldn't it just go to a lower excited state? Really good question, right? Instead of going to its ground state. We're going to answer that. The diagram to the right depicts an emission event. Okay. How does this differ from an absorption event? Oh, how would you change that diagram? Now, in an emission event, Ashley, that means that during this process, it's giving off a what? In that little picture. What is it giving off? Little wavy squiggly line and an H nu. It's giving off a... We've seen it before. We saw it right there. It is a... What'd you say? Photon. Right? Photon. Single particle, when light wants to behave like a particle, you can call it a particle. Single particle of light. Okay. What are E1 and E2? Ricky, what are E1 and E2?
Oh, crap. I think I'm going to go with Rob's answer. The first and second excited state. That's what I'm guessing.
No.
I could be wrong. You know what? Forget Rob. I'm thinking that one is the ground state and the other is an excited state.
Exactly. That's exactly what it is. Don't think too hard. It's just ground state and an excited state. Right? Does it matter which one is which? Most definitely. Right? Because this is supposed to be an emission event. So that means the upper one has to be the excited, bottom one has to be ground. Yep. And since it's an emission event, you have to draw a squiggly little line and give off a little photon. Because that's what emission is. Oh, man, yeah. That'd be a good question for this. Change this to an absorption event, right? All you do is do what Alice said, change the little arrow to the other direction, and change that little photon to go the other way to show that it's absorbed, right? Yeah, flip the arrows. That's a good one. I should add that. Okay. Oh, we didn't finish this. Can E1 and E2 change? This is a complicated question, Adriana. Can E1 and E2 change, and if so, how? But give it a shot.
He trusts you to answer.
Can E1 and E2 change?
Right now,
Yes. No, because would it require the same amount of energy to hit
Okay.
ground state to excited
that
state?
is the appropriate answer that she should be giving right now. If you've been following along everything we've said so far, you should say no to that. That E1 and E2 are fixed, right? You should definitely say no to that. However, life is more complicated. The reason why life is more complicated is when you start, spectroscopy works best in really concentrated or really dilute solutions. Which one would you guess? Really dilute. Things behave in really dilute solutions. When you start getting really concentrated solutions, things start banging with other things, and you start, this little E1, they're just getting a little foggy. E2 gets a little foggy due to those collisions. We're not worried about that, though, right? For our purposes, E1 and E2 are fixed, but just realize they can get a little foggy on you.
Okay, so they, for what we should know, they are fixed.
Yeah, they're fixed. They're fixed. I just didn't want this to turn into like analytical. Remember, I said like 5 times throughout the course we lied in general chemistry.
So the range,
Remember that?
so really the range is a little magical.
No, I would think if you are doing spectroscopy correctly, this is it,
Okay.
right? And hopefully you're going to be doing spectroscopy correctly, right? Dilute solutions. Don't worry, you don't have to worry about it. Okay. Now the idea, though, we will come back to when we start talking about atomic absorption spectroscopy. So it's kind of a lead. The reason why I brought it up, it's kind of a lead into that. Okay. We have a couple pictures here. Alice, we have a couple pictures here. We have picture number 1. Hopefully you recognize some of the things in there. Like, you recognize this guy?
Discharge.
Yeah, that discharge lamp. Okay. Then there's some funky thing in front of it. Okay. Well, this picture number 1 was used to get the results in picture number 2. What's going on in these pictures? Yeah, it's called a sort of an S spectro. No, you have to plug in a spectrophotometer. Spectroscope. Spectroscope. Okay. No, she's talking about the thing that she was looking through, right? Okay, but this guy's plugged in. You're right. Since this guy's plugged in, that is spectrophotometer of some sort, because it has to separate the wavelengths, do everything that we said in a spectrophotometer. And he even figured out what those wavelengths are. Okay. So I think we answered, Pablo, what's going on in picture number 1, right? They said this is a spectrophotometer. It even has to be plugged in, right? Well, how can you explain picture number 2?
He's taking the picture of that.
Yeah, it's taking a picture of the light coming from here.
Yeah, because when we're looking through that thing, you can see a certain number of
Yeah.
lines.
Yes.
It has to be a certain type of yeah.
It's
but
a
you're
discontinuous
using
light
it-
source.
You're using like a certain type of argon or something.
Yes. Okay, he's picking a different atom.
Yeah.
And the reason why you don't see a smear up here of colors of Roy G. Biv is because why? Yeah. All these little atoms. And Pablo picked one. He said argon. Fine. It's argon. The energy of that argon atom is, say it louder, quantized. It can only be certain energies. So it can only kick out certain wavelengths of light, right? Kick out is not the right word. We're supposed to use the word emit or emission, right? Okay. Okay. Are we good so far? So Robert, how can emission spectroscopy be used to identify and quantify the amount of cadmium in a mixture of mercury, lithium, cadmium, strontium, calcium, and sodium?
CAA2 procedures.
No, come on. Take a look at what I'm giving you. How can emission spectroscopy be used to identify and quantify the amount of cadmium in a mixture of all this other stuff? So you've got a big mess from Elmendorf or wherever. Cadmium is ugly, extremely poisonous. Well, mercury isn't so great either, but
No. But it would be more conservative.
how would you do it?
Get your lines match up.
No.
How can emission spectroscopy be used to identify and quantify? So just pick one of these, identify. How could emission spectroscopy be used to identify if cadmium's even there?
Well, would you have to know the signal of cadmium? So
I gave it to you. It's right here.
So then run your sample and see if you have those.
Yeah, like Mom said, it would match up.
Yeah.
It'd have to match up, yeah. Or you can make your life even easier.
Just
Do what?
Select that wavelength and
Select which wavelength.
the cadmium, one of those.
Wh-
'Cause I
Which
know before-
select a wavelength in cadmium that doesn't match what? Anything else. There you go. That is the most sensitive way to do it. Set that little find a wavelength of cadmium and set it at it. And even if you look at these guys, right? If you look at, it looks like these are the same, doesn't it?
Yeah.
It looks like these guys are the same, even this one. What you don't have a handle on, what you don't have a feel for, is the sensitivity and the resolution of these monochrometers. There's a mile between these two. It's no problem. Essentially, you just pick a wavelength. Now, it's rare. Since these are so narrow, it's rare that they overlap, but they do. So you do kind of have to be careful. But it's rare that they overlap. You can pretty much just pick one and do the analysis. But, I would probably look in the AA cookbook or something. Because the AA cookbook gives you, it went through all this for you, right? It tells you which wavelengths to use and even the concentration ranges. So, but essentially you can use any wavelength. But they're not all equally made. Some are more intense than others, and so there's better wavelengths than others. But okay, the amount. Let's pick on Kathleen. How would you get the amount? Okay. Okay, good. So we'll stick cadmium in. We'll stick what in the machine? The cadmium. Okay, she wants to stick some solutions of cadmium in the machine and get its absorbance or get its signal. Then what? You look at the graph. Make a calibration curve. Okay. Then what?
Yeah. Signal divided by.
Then you have to run your
Unknown.
unknown, right? And then you get the regression equation of the calibration curve and solve for x. Probably have to do what type of calibration curve? Multi-point, most definitely. But I'm thinking, what standard versus what standard? Standard addition or external standard? You can always answer what, and you're always going to be right. You can always answer standard addition and never be wrong, right? Because you don't care about the matrix. So you can always answer, do standard addition, right? You sound like you really know what's going on, right? Okay. I added this. This is why we started kind of late.
I was wondering what you were drawing.
Okay, there's a bunch of terminology here. And it's a lot easier with the diagram. So I'm going to give you some time to draw in all these little arrows and put in all the little letters. Now, Alice had a multicolored pen, so that's probably the best way to do this. But now when I turn the lights on, though, you can't see the different colors so well. All right. Want me to turn them back off
Red,
again?
blue, green.
Now they're kind of matched up. I mean, if it's the same color, it's the same letter next to it. So even if you don't have a color coding going on, the letters will match up.
You almost there.
Bacon. I think that's what A and E are for bacon strips. I know, man. I'm still furious with the that's not
It's like telling Rob you want to buy it.
even good. I heard Martis, so I was like,
Yes, I am.
what are you changing? Why are you changing it?
Well, it's not really a mistake, it's a clarification. Oh, I gotta do it again.
Funny all around. That's why I told you to use multicolored pens. He's like, I'm gonna change it. Okay, so what did I just draw that? Why did I do
There you go. Someone's thinking.
that? Don't change it.
Should F be black also?
It has a different letter name. So you're well, technically, conceptually, you could make it black.
Let's bring it in the way.
I'm trying to select, so you don't have to worry. There we go.
Thank you, sir.
No problem, sir.
All right, so we ready for this? So let's start here with. Okay, this is supposed to be a vibrational energy diagram.
Supposed to be.
Okay? And there's some things that I think need to be stated before we even start talking about it.
Like, what is it?
In our last quiz, I forget which one it was, we were talking, John, about you had different types of spectroscopy upstairs. You had UV vis, you had FTIR, but they involved different energies, different types of motion, molecular motion. Do you remember what UV vis was going on there? Does anyone remember? And what type of transitions were going on with UV vis or FTIR? That's really what I'm after. FTIR was vibrational, and that was in the infrared range, so vibrational motion, and rotational, really. And then, but UV vis was what? Electronic. Now, what was an electronic transition? What's actually changing? The what distribution? Well, here's a hint, going from one orbital to another. The what distribution? The electron distribution. Much more energetic than a vibration. So there's several different types of transitions. And you can't get away from having them all going on at the same time. So this diagram is, in that sense, kind of complicated, where you have the really dark, okay, and then you have these little thin lines, and they look like a ladder. And they really start with the really darks. Those are electronic states. So if you were on one dark line or another, right, different dark lines, the electron distribution is actually different. Okay? And the higher up you go, the higher the energy. The higher the energy. Okay? And then the little skinny lines that look like a ladder, and every single electronic state has its own ladder. The ladder is a vibrational energy ladder. Okay? So these are the vibrational energies. And then if I could really draw really super, super thin lines and have them really, really close together, in between each two vibrational lines, the vibrational ladder, I would draw a whole bunch of little dinky lines, and those are the what levels? Starts with an R. Right? If these are the vibrational ladders, I can draw more ladders inside, rotational, right? And then anything else, infinite, you can't even, there's no way. Maybe we could get little tiny lines in there for rotational, but let's not even worry about it, okay? So what is a vibrational ladder? This is a vibrational ladder, right? So for our purposes, ground state, fine. Excited state, okay? And then I want to jump up the vibrational. Notice this is all the same what, though? All the same frequency. So this is all the same frequency, right? So you can absorb a photon, h nu. And then you'll go from here to here. But you're jumping up the vibrational energy ladder, okay? Not the electronic ladder. You're jumping up the vibrational ladder. And you can jump up the vibrational ladder higher, right? The frequency doesn't change, so it's the exact same photon. You go up higher in the vibrational ladder. It's just what changed? The amplitude. So amplitude is what's changing here in the vibration. Okay, but the same frequency, same photon. Okay. Okay. So this diagram is really more set up for UV vis spectroscopy, but it would work also for FTIR, because we have a dark line, arrows going from one dark line up to, above the other dark line. So this guy must be the what state? Ground state. These guys must all be excited states because they're above the ground state, right? Okay. Now, for instrumental analysis, how do you identify singlet and triplet states, right? Using this diagram. Well, H is probably what? I is probably what? Well, these are the letters that represent the different things. So H is representing S1, H is representing S2, I is representing T1. So all of this is a what state? All this is a what state? All that guy is a what state? Singlet state. Yeah, singlet state, triplet state. Okay. Just what is a singlet state? What is a triplet state? Take pchem. Okay. But for our purposes, there's different types of excited states. Okay, there's different types. Okay. But energy is still quantized, right? There's only certain ones. But we're going to describe them as singlet and triplet states. Okay. So let's get started on this thing. We want to do some absorption. What letter probably corresponds to absorption? A. A is first off for absorption. The little arrow's pointed in the wrong way. So don't pick A. Does B make sense? Remember what absorption is. It has to go from the what state to the what state? Ground to an excited state. Yeah, so these are all absorption. Okay. And just to make this technically correct, I am going to, all right, I'm making the ground state a singlet state. Again, pchem. You can't draw lines from the ground state to the triplet excited state. Okay, and why? Well, it's pchem. There's some transitions that are allowed, others that aren't. It's weird. I mean, the energy is quantized. What's the problem? Right? But we'll leave it for a more advanced class. Just realize there's some transitions that are allowed, others that aren't. Okay. Now, take a look if this is a quiz question, take a look how to draw these arrows for absorption. They always start where?
Ground, so excited.
Yeah, but realize this, when you say ground state, it's really this whole thing.
It starts from the thick ground.
Right?
and goes into
It starts from the thick ground state. Right? That all these little vibrational ladders, you're on the very bottom here. Right? Okay. Very bottom of the vibrational ladders where you're at. And then it just jumps up, and it can go to any one of these vibrational ladders. Okay. Same with over here. Okay, that's absorption. How about fluorescence? What letter would probably be fluorescence? Oh, we're out of time. We're out of time. So we'll finish this next class. Yeah, no quiz. Look at that. We got a lot to do here.
Yeah, we have a page and a half.
No quiz?
It is a Friday. It's a Friday miracle.